Hi, my name is Chithrabhanu and I am from Center for Quantum Technologies. We are associated with National University of Singapore, and this talk was prepared for APS March meeting 2020, and my topic is conversion of position correlation into polarization entanglement. Before moving to my topic, I just want to I just want to point out we are a group which is mostly working on satellite-based quantum communication. So this is a recent deployment which we have done. So this is our satellite, and this was deployed from International Space Station, and this satellite contains an entangled photon source. So all of our effort in our group in CQT is mainly dedicated to have a better sources and better equipments for satellite-based quantum communication. So an overview of my talk is first I will be explaining you how we generate this entanglement. What are the traditional methods? And this is the method we have chosen, is the conversion from position correlation. So how the position and momentum correlations exist in this twin photons. And from I will be explaining interferometer based generation of polarization entanglement from position correlation. So this is implemented using a Mach-Zehnder type of interferometer. So this is just a demonstration, and from there we have developed a compact polarization entanglement photon pair source with the same concept. So with the same concept of interferometer, the small source, the compact source, provides better stability, so it can be used for any quantum communication. It's as a resource for quantum communication. So also this can be extended to atomic systems, so the generation process of these twin photons doesn't need to be from a nonlinear crystal which we use now. It can be from an atomic system. Also, it can be also from some quantum dots. So the method what we have shown here is more generic, and I think it can be useful in different field of research. So one simple way to address how to entangle. So I'm talking about polarization entanglement. So in the polarization entanglement, in the conventional sources, how do we generate these entangled photons? So in general, the polarization entanglement is not inherent. So we have to forcefully entangle these photons in polarization. So you can take two processes of generating correlated photons. So correlated photons means they are correlated in time, correlated in birth position, correlated in momentum. Also they are correlated in polarization. That means a signal and idler, let's say these two photons as signal and idler because of historic reasons, and if signal is horizontally polarized and the idler is also horizontally polarized. So this is generated using a type 0 spontaneous parametric down conversion. This is what we are using now. This can be different processes. This also can be a atomic decay which generate two photons of same polarization. Now so you take two processes with orthogonal polarization. That means you have one process generating two horizontal polarization and another process generating two vertical polarization. So these two processes, it may be independent, but you add them coherently, and you have to be careful about this word coherently, and then you got entanglement. So entanglement, this is it's a Bell state. If phi is 0, this is a phi plus Bell state, and you got the entanglement if we add them coherently. So this plus, this quantum superposition, is the most important, and you have to satisfy many conditions for this one. That, for example, the generated photons may not be a single wavelength. So this phi can be of different wavelengths. For different wavelength, the phi will be different, and you may have to make sure that all the phi for all the wavelengths are constant. So then you can achieve this state. So that's why this superposition should be coherent. So this coherence is plays an important role here. Right. So this is an example of how the existing sources are generated. For example, this is a Sagnac interferometer where a diagonally polarized pump is split into two, and it converts back to this is a horizontal and this is vertical. Assume this pump goes in both directions, and this is converted back to vertical because this only this crystal responds to only vertical polarization and generates two photons in both directions. So, and they add them coherently, and you can collect the photons from here. Similarly, this is the recent work which we have done in CQT. Here you have a PPKTP crystal. You split the pump photon into two. Again, similar to this one, we convert the horizontal to vertical and generate VV and VV and convert back to horizontal and combine them together, and you get the state. This I want to show you. This YVO4 is what ensuring this coherence condition, because we make sure that using this YVO4, using the correct path, the correct length of YVO4, we make sure that all the photons with all the wavelengths have same constant phase. And this is another way you generate two photons, two SPDCs using two different crystals. So you can, instead of using one crystal, you can use two crystals and combine them together. In this work we choose a different way. So we choose two decay paths produced by same SPDC. So in all of this case, there are two SPDC processes, but we consider a same SPDC process but at different position. I'll be explaining this in a minute. Before that, I just want to mention the position and momentum correlation of SPDC is well known, and it has been used for generating higher dimensional entanglement. So for example, there is a pixel entanglement, and you can follow this article for that. This is accessed using a 4F imaging system. So the position correlation is basically it tells you that if two photons are generated from a pump photon, both share a common origin. So they share a common birth position. So that it's as simple as that. And there's a momentum correlation. It comes from a momentum conservation. If single photon has one momentum, we know the momentum of the idle photon. So this is accessed using a 2F imaging system, and this position and momentum correlations are used to realize position momentum entanglement. You can follow this article, and this has applications in high dimensional entanglement, ghost imaging, etc. Now, how we are using this information, the position correlation for polarization entanglement, is by the following way. So we separate the photon pairs generated in upper or lower part of the crystal. By the way, this doesn't have to be a nonlinear crystal. It can be any systems, as I mentioned before. So consider an upper part and lower part of the crystal of any bulk material, and flip the polarization state or the photons into orthogonal state. So we choose either upper or lower, the photons generated by upper or lower part of the crystals, and flip the polarization state and combine them coherently. So that's the general method. So first of all, how to split by position and momentum. So splitting by momentum is very easy because they have different momentum. That means they travel oppositely. So if one photon travels here, the photons travels here. Splitting by position is bit different. You have to use a Forest system, and the Forest system, if two photons are generated, this is signal and idler. If two photons are generated at the top part, it will end up, if you consider a line with respect to the center of the crystal, it will end up, it exactly recreates its birth position. Similarly, the photon generated in the lower part. So it's as if looking at the crystal plane. So that's what Forest systems are for. And now you can come with any wedge-shaped mirror and split them independently. So that's exactly what we have done, and so this is how we access the position information, and this is how we convert it into a polarization entanglement. So here you can consider the crystal of with two positions, x1 and x2. x1 is the upper part, x2 is the lower part. So two photons are generated at upper part, and two photons are generated at lower part. Both has same polarization because we are considering type 0 down conversion, and times also we are considering non-degenerate and collinear. And we, as I said earlier, what we do is that we image this position onto this wedge mirror. The wedge mirror splits according to this, whether it's x1 or x2. So x1 goes to the upper part of the interferometer, and x2 goes to the lower part of the interferometer. Out of this, we convert the x2 pair to its orthogonal polarization, such as VV. So we have a half wave plate to convert it into an orthogonal polarization, while we use another half wave plate here, but it kept at 0 angle, so that it does not do any change for this photons. And we combine them together in a PBS, and also after that we couple this into a single mode fiber and split by wavelength. So you can use wavelength division multiplexer to split them into signal and idler, because as you can see, signal and idler are distinguishable in wavelength. So we measure the amount of entanglement or the quality of entanglement what we have for this state generated here, and this is the bell curves. You can see the visibility, which is an indicator for the quality of entanglement, is really high, and we get really good numbers as in terms of brightness. We get 260,000 per second per milliwatt number of photons, and the fidelity is also great. It's close to unity. So fidelity is how close your state to the ideal state. So it's almost 0.997. And only problem with this design is the stability. The stability depends upon the path length difference. So this path length difference will be converted as a phase, and the phase is not stable because these two paths are independent, and you have thermal expansion of these mirrors, and the phase will change. It will vary. So you have to lock this interferometer using a piezo attached mirror. So this, you have to use another laser to lock this interferometer. In fact, we have used exact pump laser to lock this into one constant phase. So, but this cannot be used in any quantum communication as source for quantum communication, because this is not stable. So for that we have to use a stable and compact design, and that's what we have done. So the idea is same. Instead of mapping this into using a Forest system, we split the split the photons into two different positions by coming with a segmented half-wave plate very close to the crystal. So as soon as the photons exit the crystal, it sees this half-wave plate. So in the segmented half-wave plate, one is kept at 45 degree and the other is kept at 0 degree. And this red and blue represents horizontal and vertical polarization. So here the photons which travels to the 45 degree polarizer half-wave plate converted to vertical polarization, and this is horizontal, and use a BBO crystal which has a spatial walk-off. That means the propagation will be different for horizontal and vertical. So horizontal will be transmitted and the vertical will be transmitted, and the horizontal will have an angle. So you have to choose a correct length of the BBO so that these two are combined together. And once it combined, it exists as a single beam, and we, similar to the previous case, we couple into a single mode fiber and a wavelength division multiplexer and split the Ziegler and Idler, which has both polarizations now. So these are the states. This will generate the Bell state, and we can construct the density matrix, and the fidelity is also close to 1.99, and we have a brightness which is 120,000 per second per milliwatt. This is a bit low because we are using a collimated light. The reason why we are using a collimated light is that we have an intersection here which is same as, so if you consider a Gaussian beam, the center is aligned with this intersection here, and this intersection is not perfect. So it's basically two half-wave plate, one with 45 degree and one with 0 degree placed together. So there will be a lot of scattering here. That's why we consider a collimated beam. If you focus and get a better half-wave plate, you can increase this number very much. But this is very stable. We have tested for 4 days, and it stays stable because there is no element that can change the phase, because everything is compact and there is no two different paths. There are two different paths, but it's within the crystal. So this is stable, and the performance is also really good, and it is comparable to any sources which is the state of the art. Now conclusion and some future directions. So what we have shown is that we can use the position information which is so inherent to any twin photons. So photons produced by spontaneous parametric down conversion, photon produced by decay of by hot vapor decays, all photons produced by quantum dots. So any of this heralded single photon source can be converted into a polarization entangled photon pair source. And not only that, we have shown that it can be used to generate to design a compact source of polarization entanglement with high fidelity and brightness, and this can be used in quantum communication experiments. As I said, it can be extended to other systems, and one of the applications is that you can generate an entangled photon source with really small line width, with atomic line width. Basically that's it, and this is our group, and this is the satellite which I have shown you, and just before the launch. So this satellite is a very small satellite with an entangled photon source inside, and this is our group. And if you have any questions, please ask me through email, and also you can check out our website for our activities. Thank you.